appropriate term of additive manufacturing to encompass all the different technologies that I will be describing. And these technologies have been regulated under the ISO ASTM standard on the top right of the slide. You can see there, this is still currently being revised and becoming more and more complicated, but the advantage of this standard is that it divides the additive manufacturing technologies into 7 different categories. And they are as follows: sheet lamination, powder bed fusion, directed energy deposition, material jetting, binder jetting, VAT photopolymerization, and material extrusion. Actually, if you look at the standard, they make a distinction between additive manufacturing technologies for metals in detail, the different technologies. And I will start from VAT photopolymerization, which is a rather general term that has inside, that groups inside both so-called digital light processing, or DLP, and SLA, which would be stereolithography. And the difference between DLP and SLA is simply the light source for and the way you provide radiation to your material in order to make it polymerize through radiation. SLA uses a laser beam, so it's a continuous pattern path, point-based path, continuous. And DLP rather shines a full image of the slice that you want to embed into your material. So the basic working principle for both technologies is selective curing, meaning cross-linking of a polymeric resin by means of an energy source. And you can have so-called bottom-up or top-down geometries depending on where the light source is with respect to the component that you're building. It should be noted that there are advancements in the technology that allow now the fact of using a photocurable system, polymeric system. Well, a typical mixture that would be photocurable needs to contain, first of all, photocurable monomers of oligomers, then a photoinitiator in order to start the cross-linking reaction, a photoabsorber that serves the purpose typically of controlling the penetration depth of the light inside the vat, inside the liquid. Often you have a diluent, often reactive, and then you need to add your ceramic powders, or you can have a ceramic precursor, such as a ceramic polymer or salt gel materials. And you can also have additives. So you have the problem that it is very difficult to reach full density for the component. And of course, you want to have a proper layer of powder, because if you start generating a ceramic component from a powder bed that has defects, then those defects will remain embedded in your final part, of course, compromising the properties. One advantage of this approach is that you can have very large scale printing, and there are some companies like Voxeljet in Germany that have a printer that can print sand casting cores that are up to a few meters in size. The binder that you are selectively depositing from the printing head can be either a solvent in which a polymer is dissolved. This is the most common approach. Or you can put a soluble polymeric binder powder mixed within the ceramic powder, and then you're simply printing up your solvent. Or you can use, as a printing liquid, something that would induce a setting reaction in the ceramic material. For instance, we are working with geopolymers that are bicomponent materials. We have a solid part and a liquid part. The solid part is an aluminum silicate reactive powder, and the liquid part is an alkaline solution. So we are printing using this reactive liquid, and it works pretty well. You can see some examples of some kind of casting cores made by with this technology. And people, for instance, in Schunk, they are generating components based on silicon carbide. As I mentioned, after sintering with this approach, it's very difficult to achieve full density, but then you can, for instance, infiltrate with molten silicon, and then in this way you can have a high performance, full density component. This is a heat exchanger, for instance. Once again, you can see the degree of freedom in the shape that is afforded by additive manufacturing. people are working with this approach to fabricate bioceramics. In this case, for this specific application, the presence of porosity, residual porosity, is not detrimental to the properties, but is actually beneficial because you have a higher possibility of attaching cells to the scaffolds. Inkjet printing is another technology class, and the basic working principle: you have droplets of the building material that are selectively deposited. So the difference with binder jetting is that with binder jetting approach, you're simply jetting a binder, and it can be reactive. But in this case, with inkjet printing, you're actually spraying, you're actually jetting your building material. And there's been a lot of work on making ceramic inks for printing on tiles, for instance, digital printing on tiles. And this technology has been further developed for additive manufacturing. And I would like to mention XJet from Israel, which is working on this technology. They are using nano-sized particles. So the problem is, of course, to have the correct type of particles for flowing through thin, narrow nozzles. But there are also people at IKTS in Dresden working on thermoplastic 3D printing, and they can use micron-sized particles to generate also multi-component materials and materials with a graded composition. You can see here to the right some examples of such components developed at IKTS, and these are some components made by inkjet prototyping process. Powder bed fusion is of course very famous for metal particles because you can either melt or you can sinter the metal particles with very conveniently. There is good absorption from the laser beam, laser radiation, and also high thermal conductivity, so there's no thermal shock. The problem for ceramics is that you can, in theory, reach, well, in practice also, find ways of heating up your material to either sintering or partial melting in order to consolidate the powders. But the problem is that it is very difficult to obtain defect-free ceramic parts using this approach. And the problem is mainly thermal shock. You can see here, so for instance, some cracks, residual porosity. So people, for instance, at the Belgian Ceramic Center have been quite successful in generating complex shapes using this approach, but it is difficult to have ceramic parts defect-free and full density, which is, of course, what you would like to have for most applications. And the problem with laser is the high concentrated power and thermal shock that comes with the technology. So this is, I would say, the least successful technology so far for ceramic materials. Material extrusion is another suitable approach for ceramic materials. You can either have the so-called fused deposition modeling, which would be your typical plastic printer approach, but in this way, for ceramics, the filaments contain ceramic particles. So you can imagine that in order to have a spool based on the polymer containing ceramic particles, you need a lot of plastic material, and then you have the binding problem. But this approach has been validated. You can, the printer is very cheap. You can make components. And a little bit better approach is to use the so-called direct inviting. It's also called robocasting. In this way, you generate a so-called ink, a paste that you extrude through nozzles, and you can generate complex patterns. Please note that with this approach, you have to mainly follow a continuous path. So this provides some limitations in terms of the geometry of the component that you want to build. In order to have a successful printing, for instance, here you can see some suspended features. And in order to avoid sagging of these features after printing, you need to generate an ink that has an optimized rheology. This is called the Herschel bulk fluid, where you have a yield stress, then you have pseudoplastic behavior. Basically, your ink should behave like toothpaste. When you squeeze the toothpaste, the viscosity decreases, the paste comes out of the tube, but then when it is on the bristles or on your brush, it doesn't penetrate because the viscosity with low shear stress or no shear stress increases. And this allows you to retain the shape after extrusion. And you can achieve that, this control of the rheology, either through evaporation of the solvent, or you can work with coagulation of suspension, or you can use either thermal or physical reversible gels. For instance, fumed silica forms a reversible gel with pseudoplastic rheology. You can see here an example of an ink that was not optimized, no problems for the control of the shape of the XY plane, but in the Z plane, you can see the deformation, the sagging of the structure, because the material didn't have a pseudoplastic, enough pseudoplastic behavior. But after optimizing the ink, you can see that you can retain the porosity also in the Z direction. The last technology, which I would say is not really much used, it is one of the first technologies that was tested, is the so-called laminated object manufacturing. And here you have sheets of a material that are selectively cut, typically using a laser, and they're bonded, typically thermally, to form an object. And you end up with defects at the intersection between the sheets. And also you have quite a lot of limitation in terms of the shape of the final objects. So these are, let's say, 3D, but let's say they are 2.5D structures that have been generated. So LOM is also a technology that is not really giving all the benefits of additive manufacturing. So here are a couple of slides that try to summarize the advantages and disadvantages of individual technologies in comparison to each other. So indirect additive manufacturing, heat development can also cause issues. So here is another comparison table between different technologies. I'm not going through all the details, but of course, when you're thinking of comparing different technologies, additive manufacturing technologies, you have to look at the printing envelope, so the maximum size of the component that you can generate. Then it should be noted that there is a continuous development of technologies. For instance, now people are working on making or developing technologies that allow you to have multi-material production. People are working on making continuous printing. People are working on being able to add not just short fibers, but also continuous fibers to generate ceramic matrix composites. And so the field is continuously developing. There is interest in increasing the resolution. I haven't mentioned some technologies like two-photon polymerization that would allow you to have a sub-micron resolution. Combination simultaneously enhance a combination of properties. And this is really a good way of exploiting the potential of additive manufacturing. And additive manufacturing, and I'm closing, is not just a fancy way of processing. It is now being implemented by several companies. So even people working with ceramics have to start thinking that the components that they would like to use are no longer bound by standard technologies in terms of shaping. So you can start becoming creative in terms of the shapes and the architectures that you want to exploit for improving your final product. And with this, I think I exceeded your patience and my time, and I'm open for questions.